All right, so you know that feeling, right? You're trying to snag tickets to that huge concert, the timer hits 0, you click buy, and the whole thing just grinds to a halt. Ever wonder what's going on behind the scenes? Like, what kind of digital fortress does it take to handle that insane stampede? Well, today we're going to pull back the curtain and actually design the architecture for a service like Ticketmaster.
Yeah. How do you sell a whole stadium's worth of tickets in just a few minutes without the whole thing crashing and burning? I mean, this is the million-dollar question for engineers. You've got this massive, simultaneous rush of people all fighting for the same limited seats. It's an absolute race against the clock and, total system meltdown.
And we say massive rush, we're not kidding. We're talking about potentially over 1 million people, 1 million plus, all hitting the site at the exact same second. 1 million people clicking, searching, trying to check out. The scale is just, it's hard to even wrap your head around, honestly.
This really is one of the toughest challenges in all of engineering. So, how do you build something that can stand up to that kind of pressure? Well, that's exactly what we're going to do today. We're going to design a solution, step by step, that can actually handle the rush.
Okay, let's get into it. Section 1, Blueprint for 1 billion tickets. Before we can write a single line of code, we need a plan. We got to figure out what this thing needs to do and just how big it's going to be.
So what are our goals here? Well, from a user's point of view, it's pretty straightforward, right? You got to be able to search for events and show times, look at a seating map, and pick your seats. Then the system has to hold those seats for you just for a little while so you can pay. And finally, it has to process that payment. But here's the kicker. All of this has to be super responsive and highly available, especially under that crazy load we talked about. The whole thing really boils down to reliably reserving that seat for a few minutes and doing it instantly even when everyone else is trying to do the same thing.
Okay, let's try to put some numbers to this just to get a feel for the scale. Let's imagine, say, 500 active cities with about 10,000 shows a day and an average of 2,000 seats per show. If you do the math, that comes out to roughly 2 gigabytes of new booking data every single day. And over 5 years, you're looking at almost 4 terabytes of just booking info. Getting this back-of-the-envelope math right is absolutely crucial because it's going to decide everything. What kind of databases we use, how much storage we need, the whole shebang.
All right, so we've got our blueprint. We know what we need to build. Now for the fun part, how we're going to build it. Section 2, Core System Architecture.
So let's start with the absolute basics. At its heart, any website is just a conversation, right? You've got the client, that's you, on your phone or laptop, making a request. And then you've got a server that listens to that request and sends something back. Simple enough. But a single server trying to handle 1 million people? No way. It wouldn't last a single second during a ticket rush. So what's the first step to handling all that traffic? The load balancer. This thing is a game changer. You can think of it like a super smart traffic cop for the internet. Instead of 1 million requests all slamming into one poor, overworked server, the load balancer steps in and says, okay, you go to server A, you go to server B, you go to server C. It spreads the work across a whole fleet of servers. This one idea is the absolute foundation for handling massive scale.
Now, we could build all of this as one giant piece of software, but that gets messy fast. A much smarter way is to use a microservices architecture. Just think of it like a team of highly trained specialists. We've got a movie info service that just knows about events and showtimes, a theater service that's an expert on seating maps, a dedicated booking service, a payment service, you get the idea. Each one does one job and does it well. And the best part? If the payment service is getting slammed, we can just give it more resources without having to touch anything else. It makes the whole system so much more flexible and easier to scale.
Okay, this brings us to the main event, the big one. We've got an architecture that can handle the flood of people, but how do we deal with the actual chaos of everyone trying to buy the exact same seats at the exact same time? Section 3, Surviving the Ticket Rush.
This right here, this is the question that keeps engineers up at night. It's all about concurrency. Seriously, how do you make sure that you and I can't both book the exact same seat, Section 101, row C, seat 5, at the very same millisecond? Because selling a seat twice isn't just a bug, it's a complete, catastrophic failure for a ticketing system. So what's the secret weapon? It's a powerful database concept called a transaction. The best way to think about it is like an all-or-nothing deal. You bundle a bunch of operations together, and here's the rule. Either every single step succeeds perfectly, or the whole thing gets rolled back as if it never even happened. It's this property that guarantees our data stays consistent and correct.
So let's walk through how this works for reserving a seat. When you click Reserve, the system kicks off a transaction. The first step is to check if those seats are available and, crucially, to lock them so nobody else can touch them. If they are available, great. The system updates their status to reserved, and then, this is the key, it commits the transaction. That makes the change permanent. But what if someone else beat you to it by a millisecond? Well, your check for availability will fail, the entire transaction gets thrown out, and you get that message saying, sorry, those seats are gone. It's that all-or-nothing process that makes double booking impossible.
Okay, so our system can handle the load, and it won't sell the same seat twice. We're in good shape. But we all know that in the real world, stuff breaks. Servers crash, networks go down. So for our final section, we need to talk about building a resilient system, one that expects things to fail and is designed to survive.
You know, the biggest nightmare for any big system is what's called a single point of failure. That's one little component that if it goes down, takes the whole ship down with it. The solution? Redundancy. It's a simple but powerful idea. You just have multiple copies of everything. Multiple copies of your servers, your services, your data. That way, if one of them fails, the system can just automatically reroute traffic to a healthy backup. No downtime.
And we use a few key strategies to make this happen. First, replication. That's just running multiple identical copies of our services. Easy enough. For our databases, we often use a master-slave configuration. Think of the master database as the one source of truth. It's the only one that can take new writes or changes. The slave databases are read-only copies. This splits up the work. Now, what if the master fails? That's where automatic failover comes in. The system detects the failure and immediately promotes one of the slaves to be the new master. It's all about making the system capable of healing itself on the fly.
So when you step back and look at the whole picture, you realize there's no single magic bullet. The crucial point here is that it's a combination of things. You need a really smart architecture to handle the scale, and you need robust, built-in safeguards to handle the inevitable failures.
And if you wanted to boil it down to a formula, this would be it. You take distributed microservices to handle the complexity, you add in atomic transactions to make sure the data is always correct, and you wrap the whole thing in redundancy to make sure it never goes down. That is how you build a system for the rush.
But, of course, the game is always changing. As fast as engineers build these incredibly powerful systems, you've got automated bots getting more and more sophisticated, trying to snap up all the good tickets before a real person even has a chance. So it leaves us with one final and really important question. In this ongoing architectural arms race, what's the next big step to make sure ticketing is actually fair for everyone?